I'm going to go over page 39 and 40 in the packet. It's talking about gravity versus electrostatics. Try it on your own first, 'cause it's a lot of like conceptual stuff. So whatever you don't get, I could just kind of explain. So try it out and see what you know, and I'll talk about the entire page. So first question asks, why will an isolated mass not experience a force of gravity? And the answer there is really simple, right? There's no other mass to kind of attract, right? If we look at the equation, Fg equals g m1 m2 over r squared. If you don't have two masses, right? If one of those masses is 0, you don't get any force of gravity, because Isaac Newton found that there has to be some sort of attractive property with mass. Like if you had two masses together, they are going to attract, but one mass on its own, there's no other mass to attract. And the next question asks, what's going to happen in like an isolated force or isolated charge? Is that going to experience any force? And the answer is pretty straightforward. No, there's no other charge to kind of attract or repel, right? The similarity with this equation and that equation is that there's like this sort of linear dependence on like the charge, right? If one of these charges is 0, the force is going to be 0 as well. So two charges, right, can attract or repel, but one charge has nothing else to attract or repel. I think the next question asks, 50-kilogram man is standing on the earth, like, what's the force on him by the earth? What's the force on the earth by him? And you can run the numbers. Fg equals mg, so 50 kilograms, 9.8, that should be 490 newtons. On the person, which is also going to be the same force on the earth, right? And the reason for that mathematically is, first of all, this equation, if you just multiply the mass of the earth and the mass of the person and do all of that, that's actually going to get you 490 newtons. So it's going to be the same for both, because they're like, the same mass, or like, they're I don't think actually, yeah. Why am I explaining with this equation? It's Newton's third law. It's just Newton's third law. Whatever force the earth attracts on, or whatever attractive force the earth puts on the man's going to attract back with the earth. It's just, I don't know why I'm explaining it so weird. It's literally just Newton's third law. They're attracting each other, equal and opposite force. The next question asks, hey, if you had two protons, I don't know, a certain meter apart, I can actually check right here. Yeah, I think it's like, I don't know, one meter away or whatever. Oh yeah, proton and electron, 1 meter away. What are the forces going to be on them? They're the same, equal and opposite. They have attractive an attractive force between them. This equation tells us it's the same for both, and that's just the idea of Newton's third law. All right, and we have some graphing we got to do. I didn't finish my axes, I'm sorry, but we have 4 graphs. Force gravity versus the mass, force electric versus charge, force gravity versus distance, the separation, like how far away you are. Same thing for force electric. So this, you can just do it by looking at the equation, right? So for force gravity versus mass, it's a linear thing. So if you double the mass, if you double the mass of the Earth, there's going to be twice as much force on you. Same thing for force electric versus Q, right? You can look at the equation and kind of see that, oh, Q's in the numerator, make that 2 times bigger, this becomes 2 times bigger. Force gravity versus distance, right? Intuitively thinking about it, farther away you are, the weaker the force. Closer you are, the stronger the force. Mathematically, it's an inverse square relationship because of that r squared. Same thing for force electric versus distance. Boom. So it's really kind of crazy that I don't know if you believe in a God or creator, but it makes you want to think who decided that these are going to be the same, like kind of functional dependence. It's really cool. But regardless, let's just move on to the next part, which is about these 2 protons, A and B. So the first question asks, which force is bigger, the attractive force for gravity or the repulsive force of electrostatics? How much is bigger? So what's bigger, the attractive force of gravity or the repulsive electric force? You can run the numbers. You can plug in you don't know the R, but you could plug in G, M1, M2, which is just the mass of a proton, and then you could put both technically squared because you're multiplying them both. Same thing for electric force, K times fundamental charge times fundamental charge. What you'll find, like if you, I got a pretty crazy number. This force would be 1.2 times 10 to the 36 times bigger, which is pretty crazy. And that kind of makes sense because for first of all, the fundamental charge in coulombs is bigger than like the mass in kilograms. Like this, the charge is to the negative 19th, 10 to the negative 19th. This is to the negative 27th. So that's like already like what, thousands of times bigger in terms of just like charge versus kilograms or coulombs versus kilograms. But then also this constant K is 10 to the 9th, while the gravitational constant is like to the negative 11th. So there's this idea in physics, I'm not all too familiar with it, but the idea of the four fundamental forces. There's strong force and the weak force, which have to do with like atomic, like subatomic, relationships of like, I think it's like strong force is the force that holds the nuclei together. The weak force is like, I think with decay potentially. There's also the the electromagnetic force, which this would fall under, and force of gravity. Those are the four fundamental forces. Force of gravity ends up being the weakest because, like, kind of because of that constant, like 10 to the negative 11th. You could have a whole lot of large masses, but G, that 10 to the negative 11th, kind of reduces the size of your force. So it's really interesting, but that's just, kind of an idea that, especially when you're dealing with protons and stuff, usually force of gravity is kind of neglected. Like that is so much bigger than force of gravity. But enough of that. That's not really important to know. It's just kind of cool. What happens if you replace proton A with an electron? What's going to happen to force gravity and force electric? Why? So if I were to replace this with an electron, force gravity would decrease a lot because an electron just has a lot less mass. Less mass in the system, like less of an attractive force. But the charge is the same. Like an electron just has a negative version of the charge of a proton, right? The fundamental charge. So the electric force would have the same like size. It would just become attractive. You got like now a negative with a positive. Same size force, just now attractive in the opposite direction. So for number 3, what happens if you replace this proton A with 2 protons? So this is pretty clear, like this makes a lot of sense. If you're doubling the amount of protons, you're going to have twice the amount of force gravity, right? Simply because your M1, right, for this proton, 2 protons I should say, got doubled, and your gravity is going to get double, force gravity. And the repulsive force before, right, you get 2 times the charge, so 2 times the electric force of repulsion in this case, because both are protons. What happens if you replace this with a helium nucleus? So it's 2 protons and then 2 neutrons. Force of gravity would obviously get twice as big. Well, I guess quadruple the original proton A, right? Because now, I should really make these neutrons. Now you have kind of 4 like particles. They all have like kind of the same mass. If you look at your equation sheet, neutrons of my lamp, it's the same mass as a proton. So you have 4 times the mass, but 4 times the mass, 4 times the force of gravity. But for the electric force, nothing really happened because the neutrons are neutral. They don't have any like charge, so they're not contributing to any kind of electric force. I think the last question asks, if the original protons are moved a distance 2r away, both force gravity and force electric become 1/4 the size because of that r squared. So if I make this r 2 times as big, square that, you get 4r squared in the denominator. That's 1/4 the size. And it's the same for both because they have the same r squared or inverse like square relationship. If you make it 1/3, I think the last question, 1/3 are away from each other, boom, 9 times the force. So let's head on over. How long is this video? Oh, I have a little battery. Oh, 9 minutes, that's not bad. So now point P, boom, we have in space and 3 meters to the right of this 3 nanocoulomb charge. So 3 nanocoulombs, and this other one is 2 nanocoulombs. And this is, I think, 1 meter, the other is 3 meters. So it asks, which of the following can you calculate? So if you had to calculate UE, which is electric potential energy, electric potential, the electric field, and force electric, which one can you calculate at P, at point P? You can only calculate 2 of these things, right? You can only calculate the electric potential and the electric field. Those are the 2 things that you don't need like a charge at point P at. Now you might be saying, wait, there's 2 charges. I can so do force gravity or force electric and electric potential energy, right? I have 2 charges I can plug in. But that's the force between them. I'm worried about what's at point P, right? If I put something at point P, what is the electric field going to be? Well, their electric field's always going to be there, but I don't know what charge is at point P. I can't figure out what forces are at point P. So I can only do these 2 for right now. So let's just solve for them. Voltage. Now voltage is actually, or electric potential. It's actually, I don't know if they're the same. I was taught that like voltage is a difference in potential, so I just like saying potential. But whatever. This is pretty easy to do. You just do V equals K Q1 over R1 plus K Q2 over R2. So K, right? I can actually, like, you can factor out the K whatever. You just plug in 3 nanocoulombs and then 3 meters. So remember, nanocoulombs is 3 times 10 to the negative 9th. And then negative 2 nanocoulombs over 1 meter, right? So that's just math, like a calculator thing you could do. I got negative 9 volts, which makes sense. If I were to place something here, if it was a proton, it's going to have negative potential energy because it's closer to the negative and farther away from the positive. So the positive will kind of contribute to like some positive potential energy, but it's closer to the negative. So because of that, like obviously UE UE is not like squared, but it does have like the inverse. Even though it's not R squared, it still has that inverse relationship. So negative 9 volts makes sense. For electric field, you can't simply, for electric field, you can't actually simply just say Q1 over R1 squared plus KQ2 over R2 squared. You can't do that because electric field is a vector. Voltage and potential, that's a scalar. Like that's just a quantity. It doesn't have direction. You just have potential. But electric field for sure has a direction, right? It's the direction which way a positive charge would move. So if I were to think about at point P, there would be this force, the force by the 3 nanocoulomb. So I'll say force, I don't know, electric 1. And then it's going to be the attractive force, right, if you were to put a proton of the electron. So you have to kind of do like you got to add the vectors, right, to get the total force, which involves the Pythagorean theorem, right? It's not too bad though. What you would do instead, to make it kind of easy, like it's actually a bit easy because to find the hypotenuse, right, to find that vector when you're adding it up, you just got to do this squared plus that squared equals, so I should say fx squared plus fy squared equals f squared. So, but we're not dealing with forces, we're dealing with, we're not dealing with forces, we're dealing with electric field, but same idea. So, we would really do e to the x, so ex squared, or e squared equals e to the x squared plus ey squared. So, now I'm solving for e squared. Ex, so the x component, like the x electric field, is just the force due to this. So I'll say this way, like it doesn't actually, direction doesn't, like this could be positive, sure. So we'll say KQ1 over R1 squared plus, now the y component, like electric field, is caused by the electron, so we'll say up is also positive. Because, yeah, like if I were to say KQ2 over R2 squared, and then you're squaring that whole thing, when you plug in a negative, it really won't make a difference, but yeah, we could say up is positive. Whatever, it doesn't matter. And is going to equal E squared. So I think I got E squared when I plugged everything. I think I got 333 Newton squared over Coulomb squared. And if you take the square root, my final answer, E, is going to equal 18.25 Newton coulombs. I guess that makes sense. 18 times 18. No, I don't know. But 18.25. Yeah, just some vector addition. Now, and some last questions here. For the letters you could not solve for, what information would you need? You would just need what charge that point P. So if I want to find the force, what charge is there? If I want to find the potential energy, I gotta know what charge is there. And once it's actually pretty simple once you figure out what charge, because the equation that relates electric potential and voltage and like electric field and force is like, yeah, force electric equals Q times E. UE equals Q times V. So these are the equations that relate voltage and electric potential energy, electric field and electric force. Like it asks, like, well, what happens if you put a positive 1 Newton Coulomb charge? Just take your answer and then put in 1 times 10 to the negative 9th, right? Put in negative 9 volts, multiply that by 1 times 10 to the negative 9th, you get your potential energy. And it also asks, like, oh, which way would it move? If it's a positive charge, right, it's just going to go in the direction of the electric field. So, like this way, which makes sense. It's getting attractive while also getting repelled. So it's going to kind of curve, or not curve, but yeah, curve that way. While as an electron, if you put a negative, or not an electron, but a negative 1 nanocoulomb charge, it's negative, going to get repelled by the top charge, attracted to the right charge or left charge, so it's going to curve kind of the opposite way. So hopefully that made sense. Let me know if you have questions, or let Mr. Gustin know you have questions. He's probably a better teacher. He is a better, I don't know what I'm saying, probably. He is a better teacher than me, but I tried. Thank you for watching.